Hello and welcome to our last topic of the unit, which are intermolecular forces or attractions between molecules. So I'm going to put these into mainly three categories to allow you to kind of compare them. Some of these you need to know a little bit more detail about than others. This is really on more of a continuum, so I treat these like they're three categorized types of forces, but you can have kind of a degree where they sort of cross the border a little bit. So the very weakest types of forces are actually referred to as van der Waals forces. You do not need to know the name of this type of force. You just need to understand why these forces are weak in terms of the molecules themselves. Van der Waals forces are going to occur in nonpolar molecules and noble gases. So I gave you two examples up here. If you look at a nice nonpolar molecule like H2, these two H2 molecules, their electron clouds are so symmetrical that they don't have any regions of charges on them. Because they have no regions of charge, they have no way of attracting one another. So there's really no way that they can easily attract one another because there's no charges involved. We have a very, very symmetrical molecule with an even distribution of charge. When you look at the noble gases, those are spherically shaped, they're monoatomic, so again, they're extremely symmetrical and they have no real way of attracting one another. These elements are going to have low boiling points and low melting points. They don't have any good way of attracting each other, so it's just easier for them not to attract each other and be a gas. They're all gases at STP, and they're considered to have very weak intermolecular forces. We can have what are called moderate intermolecular forces, such as a dipole interaction. This is not a need-to-know term, but one that's kind of nice to use. Molecules that are moderately polar, things like HCl is another one we talked about, HBr we have up here. When we look at the electronegativities of the atoms involved, so hydrogen's got an electronegativity of 2.2. Bromine has an electronegativity of 3.0. So electrons are being pulled toward bromine a little bit. We also have these lone pairs that you're seeing here. What that creates for us, whoops, I did not mean to get rid of those electrons. What that creates for us is a couple of regions where we have partial positive and partial negative charges. And this is not a symbol you need to know either. It's just kind of a nice way of looking at this. So it gets a little bit positive by hydrogen, and it gets a little bit negative by bromine. And the reason that this happens is because hydrogen's electrons are being sucked towards bromine. So what that's going to create between these two molecules is an intermolecular force of attraction that we refer to as a dipole molecule, or a dipole interaction. Again, you don't need to know that term dipole interaction, but you should know that moderately polar molecules are going to have interactions that occur because we have charged regions in our molecules. So these are polar molecules because they're asymmetrical. They have what we call a dipole. They have charged regions. Those charges are able to attract one another. So this can, easily be seen too. We drew those electron cloud pictures before. You can kind of see that around bromine right there. That extra density of those lone pairs, it's pulling electrons towards it from hydrogen. So it gets a little negative on this end, a little positive here. We see that attraction occurring. These molecules are going to have moderate boiling points and melting points. Some of them will still be gases at STP, but they tend to be able to be made into liquids. Many of them are actually liquids at STP. HCl is actually a liquid at STP, but then very easily vaporizes. They have moderate intermolecular forces, is what's really important here. The one you need to know the most detail about, including its name, are what we call hydrogen bonds. This is a misnomer. People are like, oh, hydrogen bonds, that bond between two hydrogens. No, it's not. A hydrogen bond is actually not even a bond. It's an intermolecular force. So in a hydrogen bond, there is hydrogen involved in it, just not maybe in the way that you might think. So when hydrogen bonding occurs, it occurs in the three molecules that are given up here, which is H2O, NH3, and HF, and you do need to know those. So if you take, for example, water, this is actually the reason that water is a liquid temperature and why we're able to live here on the planet Earth at all. Within water, we have our electronegativity of oxygen, which is pretty high. This is 3.4, and our electronegativity of hydrogen is a little bit lower. It's 2.2. That's a pretty substantial electronegativity difference, and oxygen pulls hydrogen's electrons towards itself. And it has that extra cloud of lone pairs. So we actually get a very strong partial negative charge and a very strong partial positive charge. One electron is a unit of one charge. This charge right up here is not one full unit like an electron, but I believe it's something like 0.8, like it's real close. So you actually have an attraction that's almost as strong as an ionic bond that is going to occur right here between those guys, and that is a hydrogen bond. Again, not really a bond, it's a misnomer. It's an intermolecular force. And it really has to do with oxygen being really small and just sucking all those extra electrons over by itself. A similar thing happens in ammonia. You have a partial negative, partial positive, partial negative, partial positive, and this is a very highly polar molecule, just like water. Nitrogen is small and has a high electronegativity, so it pulls electrons towards itself. So we're going to get a hydrogen bond occurring there. The same thing's going to happen in HF. Remember, F is very small, and its electronegativity is 4.0, so you're actually going to have hydrogen bonding there as well, because it's pretty positive by the hydrogen and pretty negative by the fluorine. So this really has a lot to do with the high electronegativity and small size of fluorine, oxygen, and nitrogen. It creates a very strong, very large electronegativity difference and a highly polar bond, and a highly polar molecule also. So these are very polar molecules. To really contrast this for you, you do need to know that the strongest intermolecular force we talk about is called hydrogen bonding. You need to understand that it's not an actual bond. You need to know that these three molecules do hydrogen bonding, and they're considered really polar. Then you need to also know that you have other polar interactions, but they're just not as strong. These are considered moderately polar molecules, so this is a less strong intermolecular force because your charges just aren't as strong. What's really cool about hydrogen bonding is it's extremely strong. I really like this graph. I found it somewhere, and I like what it actually shows in terms of groups. So if you look at the red line up here where you're comparing H2O, H2S, H2SE, there's something, group 16, group 16, group 16. So we expect these compounds to be fairly similar to one another in terms of how they behave. What we find out here, if we wanted to compare H2O and HS, for example, both have something from group 16 in them. They both contain two H's. They both contain a group 16 element. O versus S is the difference. If we want to look at our gram formula mass for these, for oxygen, we have 16 plus 1 plus 1, which gives us 18 grams per mole. For sulfur, 32 plus 1 plus 1 gives us 34 grams per mole. The electronegativity difference in the bond is extremely telling here. So when we look at our electronegativity difference between oxygen and hydrogen, we do 3.4 minus 2.2, we get a difference of 1.2. If we look up sulfur's electronegativity is only 2.6, so the difference is only 0.4. That's a pretty small difference. So we create that really high level of polarity in water that makes water a liquid at STP. Hydrogen hydrogen sulfide is actually one of the gases given off by volcanoes. You'll notice its boiling point is way below zero, according to this graph. So it's actually a gas at STP. You might think, so what? Big deal, who cares? This is really important because the trend that we really expect is that there should be a linear relationship of the boiling point of these compounds. And they extrapolated this down here to show that really the estimated boiling point of water, if hydrogen bonding didn't occur, would be at about negative 100 degrees Celsius, which would really put us in a rough spot here on Earth where water would not be able to be a liquid. When you look at the fact that hydrogen sulfide is so much quote-unquote heavier in terms of grams per mole, it would make more sense for that to be a liquid than something lighter like a water molecule. It's easier to float away, you would think. But those strong intermolecular attractions give water that very, very high boiling point. You can see the same trend occurring if you look at your hydrogen with group 17. Hydrogen fluoride has that hydrogen bonding. It's got a way higher boiling point than the larger molecules involving group 17 ions. So very interesting graphic that kind of actually predicts how we're able to live here on Earth. So hydrogen bonding is responsible for the very high boiling point of water and the fact that water is a liquid at room temperature. Very important chemistry theme. Intermolecular forces are forces between molecules. They affect boiling point and phase matter. Here's the deal, so we'll kind of continuum for you. Weak, IMF. Medium, IMF. Strong, IMF. And specifically here we are talking about hydrogen bonds. You don't need to know the names of the other ones. Weak intermolecular forces are going to give you low boiling point, strong, high boiling point. Weak gases at STP, strong, more likely to be liquid, potentially even solid. Most of the things we're talking about are going to be liquids. Very often in the middle, you're going to run into moderate boiling points. Very often easy to evaporate liquids. Remember, you do need some degree of polarity there, so you can also relate this to polarity. So these are completely nonpolar molecules. These are sort of polar molecules. These are strongly polar molecules. Specifically, and you need to know them, NH3, H2O, and HF. One thing that I would like to tie into this too is the idea of vapor pressure. With weak intermolecular forces, you're going to have a high vapor pressure. We talked about this in another unit. These are going to be your liquids that have the lowest vapor pressures because you don't have a lot of evaporation there. Those molecules hang on to each other very strongly.